Hi, we're back here at Hudson Valley Statistics 220, and I know the last couple of chapters were a little challenging. This one also, but if you remember a couple of the rules, there's really only three formulas, three or four formulas you have to remember. Okay, I hope you have printed out a handout for Chapter 9, which is called Confidence Interval, so you can follow along. Again, you can pull up my PowerPoint presentation on Blackboard to also reinforce what we're learning here. And always don't forget to do any of the homework problems I've assigned. That will also help you. So at this time, I am going to go over to the DocCam to do some of the problems. So there's handout for Chapter 9, Confidence Interval. And when I say confidence interval, that means you are going to give me two answers. Okay? Two answers. And there's really three different types of problems. Okay? There's three different types of problems. And you need to understand the notation. For example, X bar means sample mean. Mu is the population mean. Very often we only have the sample mean, so therefore we estimate the population mean from the sample. The other really more critical vocabulary is the first one is standard deviation population. S is standard deviation of a sample. If in the problem I say the standard deviation of the problem, of the population standard deviation is 5, for example, you will use the Z table or critical Z values. If I say in the problem the sample standard deviation is 2, you need to go to the T table. Those are two critical rules you have to remember. Now, when we go to the Z, I have summarized those for you. I have summarized in my chart at the bottom, I have summarized the critical Z's. In Chapter 9, we will only use two-tail. In Chapter 9, we will only use two-tail. So if I say I give you the population standard deviation to look up the Z value for 99% confidence, it would be 2.575. 95% confidence, 1.96, and 90 is 1.64. So this is where you find it. Okay. Perhaps if we just go to a problem, that will be the best way for you to understand. So the first problem I have here, and you'll notice on the handout I say we know the population standard deviation. Immediately you should say, oh, that's going to be a Z confidence interval. So let's look at this. The American Management Association wished to have information on the mean income of middle managers in the retail industry. A random sample of 256 managers revealed a sample mean of 45,420 and a standard deviation of the population of 2,050. The association would like to answer the following question. Typically on this test, I'm going to say, what is the population mean? You'll see that. We don't have it. I'm going to write the givens here. The first thing I have is a random sample of 256. I have a sample average of 45,420. I have a population, so I'm going to use sigma, not S, standard deviation of 2,050. Okay? This is all I say, what is the population mean? We have the sample mean, but that will be our best estimate of our population mean. So when I ask this on the test, you're just going to give me the sample mean. Okay. 95% confidence. Because we have the population, you look for the z-value, 95% confidence interval. All you do, you don't use 95% in the calculation. All you're doing is finding the z-value associated with that. So we have 95% 2 till 1.96. 1.96. Well, to develop the confidence interval, now here's where I want you to pay attention. No, I want you to pay attention the whole video, actually. If you look at my chart, I say confidence interval. Chapter 9, you can bring this to a test. We are going to use this formula, or this formula, or this formula. Right now, since you know your population standard deviation in this problem, it's 2050, we are going to use that confidence interval formula. So I'm going to copy it right down here. X bar plus or minus z. Remember, standard error of the mean. Okay. I'm going to substitute it in. 45,420 plus and minus our z value, 1.96, times the standard deviation divided by the square root of the sample size. Okay? When we do this calculation, don't forget to add this to the mean and subtract this from the mean. So you're going to get two answers. Well, if you do it correctly, you're going to get 45,420 to 45,671. What does that mean? I say, what do these results mean? It means I can be 95% confident that if I sample 256 middle managers, the average salary will fall in between there. And that's a little different and even better information if I say, oh, the average salary is 45,420. Well, how much does that vary? Well, I can tell you I'm 95% confident it's between there. Okay, that is the application when we use the Z statistic, because I knew the population standard deviation. Let's go on to the next type of problem, which is the T distribution. I'm going to fold this in half so you can see it better. The bottom. We're going to look at this example here. A tire manufacturer wishes to investigate the tread life of its tires. A sample of 10 tires driven 50,000 miles revealed a mean of 0.32 inches of tread remaining with a standard deviation of 0.09. Construct a 95% interval for the population. Okay, let's write the givens. We have a sample of 10. We have a mean of 0.32. We have a standard deviation of 0.09. Is it a population or a sample? Well, if you notice here, the word sample is in the sentence with standard deviation. They sampled 10 and they got these two statistics, the mean and the standard deviation. So this is a sample standard deviation, or an S. We want a 95% confidence interval. Okay, so our decision is which of these formulas to use. Well, we don't know our population, so we're not going to use the Z formula. We know our sample standard deviation, so we're going to use our T statistic. By the way, ignore this up here. We're going to use our T confidence interval formula with our sample standard deviation known is a T. So I'm going to write that. Now, if I ask you what is the best estimate of our population mean? Well, this is our sample mean. Once again, the best estimate of our population mean is our sample. So we put 0.32 plus or minus T. Ooh, new table here. T table. It's the second page of your 4 pages of table. T table. T table. What two pieces of information do you need? You need the degrees of freedom, and here, two-tailed, our confidence interval. Now, you are welcome onto degrees of freedom right above here. Degrees of freedom are equal to n minus 1. You can write it right on there and bring it into the test. So, we have 10 sample size, our degrees of freedom n minus 1, 10 minus 1. So our degrees of freedom are 9 at 95% confidence interval. So let's look at this. 9 degrees of freedom. We want to be 95% confident. 95% confident. We come up here 2.2622. Again, degrees of freedom, 10 minus 1 is 9. 95% confident, come up here, 2.2622. 2.2622 times the standard deviation of 0.09 over the square root of sample size, which is 10. When we do this calculation, again, remember to add and subtract, you're going to get an answer of 2.56, and when we add it, it's 0.384. We can be 95% confident that after we drive 50,000 miles, the amount of tread remaining is between 2.56 and 0.384. Well, the question asked, would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount is 0.30? Yes, because it's falling in between these two amounts. So yes, it is reasonable to bring it home, that there'd be that much tread remaining. Okay, so we've done a Z and we've done a T confidence interval problem. The next one, and I'm only going to do one of each in your PowerPoint, in my PowerPoint presentations, I do a couple examples of each, but I'm just going to do the first example here. So let's go to question number 4. And it's a proportion example. The union representing the bottle blowers of America is considering a proposal to merge with the Teamsters Union. According to BBA bylaws, 3/4 of the union members must approve it. A random sample of 2,000 members revealed 1,600 plan to vote for the merger proposal. what is the estimate of the population proportion? Develop a 95% confidence interval for the population proportion. Basing your decision on this sample information, can you conclude that the necessary proportion of BBA members favor the merger? Okay, first thing we always write is our given. In proportions, we have to calculate the proportion. Here, it's X over N. In this example, 1,600 will vote for it out of a sample of 2,000, or 80%. What is our confidence interval formula for a proportion? Since we're dealing with percents, P plus or minus Z times the standard error. 1 minus P over N. That can be found here. Proportion data, confidence interval, and we come over here is our formula for confidence interval for proportion or percent data. So, when I ask what is the estimate of the population proportion, well, we have this sample proportion now, that's 80%. That will estimate our population. Just like I had on the other two examples, the sample is the best estimate of the population. Okay. The other piece of information, 95% confidence interval. Well, we always use the Z statistic for proportion. So I want to be 95% confident. Right now we're only dealing with two tails, so it's 1.96 again. So Z equals 1.96. Okay. Now we have everything we need to substitute into that formula. We have the estimate of the population plus and minus Z, 1.96, standard error, which is, we repeat, 0.80, 1 minus 0.80, over the sample size, which we found was given, 2,000. I want to emphasize your estimate of a proportion, or this P that's 3 places in the formula, it will always be between 0 and 1. It's a proportion. It's a percent. It's not, very often students during the test will put like 1,600 here. It can't be. It's a percent. Way back in chapter 5, I told you a percent is between 0 and 1. So when we do this problem, we add and subtract, we get a range of 0.782 to 0.818. So I can be 95% confident that the people that will vote for this merger are between 78% and about 82%. Well, they only needed 3/4 or 75%. So yes, the merger will, it's most likely, or 95% likely, that they will approve the merger. That was a proportion problem. Okay? Now I'm going to quickly, down on this sheet here is called FPC. We're going to talk about this correction factor. And what happens is, on all 3 of these formulas, remember, this portion is called the standard error. Standard error, standard error. Because we're sampling, there's a standard error. However, sometimes we sample a large portion of the population. For example, I might sample only 4 out of 100. I sample 4 people out of a population of 100. That's only 4%, right, of my population. I want to use the entire error, or 100% of the error, in my confidence interval formulas. However, if I sample 25 out of a population of 100, I've sampled 25% of my population, and I want to reduce this error. How do I reduce this error? Each one of these formulas, I will attach this FPC down here. See this? I attach it. So, for example, on all three of those formulas, when I sample over, if the sample size over the population, for example, I said I sampled 25 over 100, or I sampled 25%, use or attach the FPC, which is n minus n over n, where this is the population and this is the sample. So instead of using, for example, that formula, if I choose that formula, I would do that. I would multiply it by this. If I choose that it's a T formula, I would attach it to the T formula. If I decide it's a proportion problem, I would attach the FPC to the proportion. And this is the FPC. This is it. And what it does, it reduces the effect of the error. So I'm going to do one problem. This concept, you'll have to talk to me during the semester. Sometimes I require that I do include this on your next test, and sometimes I don't. So we will have discussions in class or online about whether the FPC, but I wanted to include it in the video because very often I do include it in the test. So let's look at example number 8. Example number 8 here. There are, I'll make it a little bit easier for you to see here. There are 250 families in Scandy, Pennsylvania. A random sample of 30 of these families revealed the mean annual church contribution was 400 and a standard deviation was 75, with a 90% confidence interval. Okay, that's an addition. The question, could the population mean be $445 or $425? Again, the first question I will ask you is, what is the population mean? Okay? So, let's write the givens. There are 250 families, so that is the population. Random sample of 30 of those revealed a mean church contributions 450 and a standard deviation of $75. Is this a population or a sample? Well, let me think about that for a second. It's a sample because the word sample's in the sentence. Okay, what is the population mean? Well, I don't know it. I know the sample, so I estimate it. Mu is the population. The estimate of the population mean is from the sample 450. The other thing you want to think about, I've never given you population before. So you want to check to see if we use the FPC. N divided by N. 30 divided by 250 is 12%. If you look at my guidelines, I say use the FPC if that percent is above 5%, which it is. We're at 12. So, since we have the sample standard deviation, we use a t-distribution. There's our confidence interval formula. But since we've sampled 12% of the population, I am going to attach the FPC. So to substitute 450 plus and minus our t value, let's look it up in our t table. We have degrees of freedom of 29, confidence interval of 90%. So our t value is 1.6991. Standard deviation is 75 divided by the square root of the sample size. And now our FPC, 250 minus 30, 250 minus 1. When we do that calculation, I don't have the answer to the calculation, but what I recommend you do is you do this calculation, write it down, do this calculation, write it down, then multiply all three of those. Then you will add it to 450, and then you will subtract it from 450. So there's a quick explanation of where to use the FPC, finite correction factor. The last thing I want to go over in this chapter is sample size, N, finding sample size. Okay? And if you turn to the last page of your handout, sample size determination. There are two formulas that, and I'm going to write them down here. Well, you know what? I'm going to write them right above it. Sample size. There's one for mean. Sample size means N. If I ask for the sample size, you're looking for N. There's one formula where you have Z times the standard deviation, population or sample, divided by E squared. Oh, we have a new variable here, E. It's the maximum amount of allowable error, okay? The E will be denoted by error, or plus or minus $5, or within a number, okay? E is the maximum amount of error. That's one formula. The other formula, when we have proportion data, is P, 1 minus P, Z divided by the allowable error squared. Don't ask me why this whole, students only square part of it. You square everything in the parentheses. So let's look at our first example. A student in public administration wants to determine the mean amount of members of city councils in large cities earn per month for being a council member. The error in estimating the mean is to be less than $100 with a 95% level of confidence. The study found a report by the Department of Labor that estimated the standard deviation to be 1,000. What is the required sample size? Since I gave you the standard deviation, you're going to use that formula. So Z for 95% is 1.96. Standard deviation is 1,000. And E is the error, $100. So sample size, 1.96 times 1,000 over the allowable error, which is 100, and don't forget to square. When you get this, listen carefully, you get 384.16. When you do sample size, it breaks the rules for rounding. If you get anything there, you always round up. So the required sample size is 385. You've got to round up with any little bit there. Let's look at the other type of problem. The American Kennel Club wants to estimate the proportion of children that have a dog as a pet. If the club wanted the estimate to be within 3% of the population proportion, how many children would they need to contact? Assume 90% level of confidence, and the club's estimate that 30% of the children have a pet. Well, all of these proportion, percents, we are going to use N equals P, 1 minus P, Z over E squared. What is P? The estimate is 30%. Put it in decimal form. Z, for 95% confident, 1.96. Error, 0.03. So substitute it, let's substitute it right here in our formula. 0.30, 1 minus 0.30, Z of 1.96 over the error of 0.03 squared. Squared. When you do that, you get 897 samples. Okay? So I've done an example of one of each type. It's very important, I want to end with this, it's very important that you understand when to use these three formulas. Okay? We start off here in Chapter 9 with confidence interval. If we know the population standard deviation, it's a Z. If we know the sample standard deviation, it's a T. If we have proportion data, it's the proportion confidence interval. It's very important you understand when to apply those. If I ask for confidence level interval, you're going to give me two numbers. Those concepts, whether to use the Z, T, or proportion, we are going to use for the next couple of weeks in Chapter 10 and 11. So I want you to be confident. Please do the homework. Please do the homework. Those concepts are going to be applied in hypothesis testing in the next couple of chapters that are really I want to say the meat and the potatoes of statistics. It's what people really do is hypothesis testing when they're testing medication, when they are looking at elections, when they are test marketing new products. They use hypothesis testing. And I'm going to try it over the next several chapters to use business applications so you understand where they're applied. Again, if you have any questions, you're welcome to email me or contact me, give me a phone call, stop by my office hour. Hope you have a good day and enjoy.